Let me introduce to the fission concept. Now in the fission, what happened? A heavier nuclei, so like a uranium, that particular thing will break up into middleweight, and the more popular is what? And the more popular is what we have there. Barium and krypton is what usually they're very popular. That will be taking for example here. So basic fission reaction, breaking up into parts. That's called like a fission here. Suppose there is a uranium nucleus. Uranium 235 92. When it absorbs slow moving thermal neutron, this is like a thermal neutron. Now what is the energy of this? Should be 0.02 electron volt. Look at this, almost at rest, no? Slow moving. I'll better introduce the word. When this uranium 235 captures slow moving thermal neutron, then what will happen to is it will become uranium 236 92. Then we'll get a fragments, barium. And these are very popular in books we have taken. So altogether around some 72 different types of fragments will come. At least some in books we have given around some 10. I'll write down tomorrow that one. And on an average, 2 neutrons and plus energy will be released. So these are the fragments. And these are the high-speed neutrons. Uranium 235 on its own will not undergo fission. When it captures the slow moving thermal neutron, it will undergo fission. So what actually happens is like the nucleus will be like this. There's a uranium 235. The moment this is captures neutron, when it captures the neutron, then it will become uranium 236. Then what happens here, the division will not occur suddenly. So gradually the shape changes. The shape changes. Then after this, this is what happens to the nucleus. Then finally what happens, it will break up into fragments. These are the fragments. So you can put barium, krypton. At final one point, we have to again go to the inside the nucleus. We don't have any particular knowledge to get into the nucleus and work out here. So this uranium 236 is highly unstable, and uranium 235 cannot break up on its own. I think this is very important. When it captures slow moving thermal neutron, fast moving thermal neutron, again it will not undergo disintegration like this. It cannot capture uranium 235 if it can capture only slow moving thermal neutrons. If it captures fast moving thermal neutron, it will become some other thing, some other phenomena that later tomorrow we'll discuss here. When it captures slow moving thermal neutron, it will become highly unstable. The nucleus what happen itself will break up into 2 middleweight nucleus. These are what? Fragments which will come in middleweight nucleus. When I check the binding energy of these fragments, no, is greater than that of the uranium. And with this what happen, an energy will be released here. To get energy, why fission then? To get energy. Why fission means to get energy. So because energy will be released, and that energy what I'll use for applications. Means now you can ask questions. So kerosene is there, I'll burn kerosene, I'll burn petrol. What for 1 liter kerosene, what you burn the energy, no? For the same 1 liter, what happen, you get almost some around 10 to the power of 8 times of energy. What you burn 1 liter petrol, what you get energy, and what you burn 1 liter of uranium, let's assume. you get almost some around 10 to the power of 8 times. That much of high energy is what available here. Means from where that energy will come. Therefore, the nuclear energy is what we are going to utilize here. And these are what? High speed neutrons. There's some books open what they made 141 they wrote. See, you don't get confused. If you write, if I make this 141, this will become 3. So don't again, anything can possible. Or some books they wrote 142. They made this 91. It can happen. There are around 70 combinations are there. Not 1, 2. Uranium must undergo barium krypton only. It all depends. The most popular what we are using in the book is, don't say again, most of the fragments are barium krypton, not like that. The most popularly what we use in the book is this one. That's why we are just showing in terms of that. Some books they show 2 neutrons, some books they are showing 3 neutrons. Okay, this neutron captures this one. Next again, we want a chain reaction. Like that, I can't send one thermal neutron because uranium-235. Can I isolate one atom? Not possible, no. Usually what we get uranium substance. That's all. There's a uranium block and that's a uranium ore. It is. Uranium oxide. This was the uranium ore, no? What it contains? Uranium-238 and uranium-235. What is the percentage of this? Will be around 5%. This will be 95%. Which is particular thing what we are using for application? This one. So if you go for enriched uranium, enriched means where you are going to increase the percentage of uranium-235 in this uranium ore. Then it will become a little bit costlier. So 1 kg of uranium, it will cost in the market around 42,000 rupees present rate per kg. 1 kg of uranium. And this much of, it's a very cheap. 1 kg of uranium will cost you in the market. It's not available. It's very difficult to acquire this uranium. So 42,000 rupees, and if it is more enriched, little bit cost will increase. But altogether, the maximum possible enriching what we can bring it at the most maximum to 20%. That's all. Beyond that, not possible. The uranium ore. The more enriched, little bit the cost will increase. Maybe it may go to up to 2 lakh. That's all. 2 lakh rupees per kg. But that 1 kg uranium is something is very bigger. It will generate a huge amount of energy. We can a huge amount of electric power we can generate here. So how it is possible? So for that what happen? I want chain reaction. Chain reaction means what I should do. Again, these neutrons should go and should be captured by uranium-235. And for this fission will occur only when what happen? When uranium-235 encounters slow moving thermal neutrons. So this has to be slowed down. No? So in the chain reaction, in the nuclear reactor, what I should do? These neutrons which are generated by uranium-235 fission reaction, again what happens? They should only use it for the reaction. So what is the next duty? I should slow down these neutrons. For this what happens? I'll go for the moderators. I should decrease the kinetic energy of neutrons. So what are the best things? I'll go for moderator. At the same time, I should also control the reaction. So how to control that reaction? By controlling the number of neutrons available. So for that weapon, I'll go for graphite or boron rods. What they do, they will absorb neutrons. Means if you send neutron and let it strike the boron or the graphite rods, so they will absorb it. They're good absorbers of neutrons. So like that weapon, I'll go for control rods. So using control rods weapon, I can control the number of neutrons. Using moderator. What is a moderator? Which will decrease the kinetic energy of the neutron. Example, heavy water. Using heavy water, deuterium, I can decrease the kinetic energy of neutron. When the kinetic energy of this neutron decreases, so once the kinetic energy becomes very small, then when the energy of them of order 0.02 electron volt, again when those neutrons, when they pass nearby uranium, the uranium will capture it and it will undergo fission. So how to make the chain reaction? The fast moving neutrons which are generated in uranium fission, they should be slowed down. And those neutrons, if they again, they're incident on the uranium-235 nuclei, the reaction, the chain reaction will continue. So like that what happen? So for the nuclear reactor, what is essential? Chain reactions should occur. You just start the reaction and it should continue. For that purpose, this neutrons becomes very important. I should able to control the reaction amount of how many fissions will occur, and also what will happen. Like I should able to control the amount of fission, and also if I'm permit what happen, I should stop the reactor. No, so if I remove all the neutrons from the reactor, as the fission will stop it. So like that what happen. It's all about this neutron, nothing to do with uranium. So how you manage these neutrons, based on that, the reactor will work out here. What about, sir, how to calculate energy relief? Again, if they give masses, mass of parent minus mass of daughter will be energy. If they give binding energy per nucleon or binding energy of daughter more than that of parent, energy will be released here. Like that, per fission will calculate energy. Then we'll go for 1 kg how much of energy. Like that, we can proceed further. I think tomorrow I'll continue. Time is already 1. Tomorrow we'll discuss the numericals on this. Thank you all of you. Okay, thank you all of you. Yeah, bye. See you.
Sir,
Yeah.
can you open the first page?
What happened?
Sir, it should be Q is equal to Kx plus Ky, no, sir.
What happened? What is the problem? That incident particle will come also with kinetic energy, no? Total energy should be conserved.